Thank you so much again for the introduction. So for today's talk, um, we're gonna, as I said yesterday, upgrade the class that we built in last lecture, which I denoted by omega chi et al. This was Y is a Siegel threefold with appropriate level structure with coefficient in QP3 uh, to a class, to an integral class. So I will denote it by the same symbol. So H3 et al. Of Y ZP3. Okay, so this is the objective of today. And the precise plan for today's lecture is going to be as follows. First, I will talk about what I call the Faltings lattice. This is a specific lattice in coherent cohomology that I will explain. And then I will talk about the integral Faltings extension. And then finally, I will give the applications, not only to upgrade the class, but also talk a little bit about what the applications of this, the Euler system that we built using these classes is, and maybe if I have time also about what this general framework of the integral Faltings extension allows you to prove, uh, when it comes to, um, say, generalizing Oda's theorem for more general Shimura varieties. But this I don't know if I will have time to talk about. In any case, so this will be the sort of most technical talk, and the first part. So when I talk about Faltings lattice, I'm gonna try to motivate the subject. Okay, so Faltings lattice.
Yeah, Marco, can you share
Yeah.
your screen once more? The screen is not shared.
Oh, the screen is not shared? Oops. Let me try to lancer la diffusion. Sorry, it got, I don't know why.
That's fine. Yes.
Can you see it now?
Yes.
Yeah, okay. So so in the first part, as I said, I will try to um, motivate what we're trying to do. Okay, so let me talk about Faltings lattice. So as before, let me just remind you about the class omega chi et al. So it's a class in the H3 et al. Of Y with QP3 coefficients that was constructed from a Durham class, a three form from a differential omega chi, which was e chi z dz. Z is the variable on the Ziegerhoff space of genus 2. And so e chi z was the non-absolutely convergent series. Here we have a normalizing factor, and then a sum over pairs of 2 by 2 matrices, chi of that C. And then here I have that of CZ plus D to the minus 3. So this was my Ziegler-Eisenstein series. And it turns out that when one computes the Fourier expansion of E chi z, this is because E chi z plus x is E chi z for any x that is a 2 by 2 symmetric matrices with coefficients in z. So when you compute the Fourier expansion, which I call the Fourier expansion at the infinity cusp, so E chi of q, it's going to be the sum over t, some sim2 of z, or rather the dual of this, but and the coefficient will be indexed by this symmetric 2 by 2 matrices, at, and then q to the t, so formally. And it turns out that this at belong in Z chi, which is the ring of integers of q chi, and q chi from yesterday's notation is just a field where you have joined the values of chi. So when P does not divide the conductor of chi, this implies that E chi, so this was denoted by big N, defines a section. So if I see E chi as something that lies in the H0 of Y, omega 3 of Y, then it actually lies inside the smaller space Y curly omega 3 Y curly, where Y curly is a smooth model of um, of the Siegel variety over Z invert 1 over N. So in particular, so this lies in, so if I tensor with ZP everywhere, the E chi lies in the lattice. So lattice H0 of Y omega 3 of Y, tensor Z ZP inside the H0 of Y omega 3 of Y tensored with QP. Okay, so this is sort of the natural lattice uh, inside this space when you have an integral smooth model. So this is smooth, and this is the key to applying the Q expansion principle with the reducibility of the Igusa tower. Okay, so but now the whole point of the Euler system, so two problems. So the first one is we want to go up the P tower. So this means that chi should be highly ramified at P, should be, you need to allow this condition if you want to build an Euler system with p-adic variation. And so what happens? So what is a natural integral structure on H0 of Y omega 3 of Y? So I will view now Y over QP, okay? So this is a QP vector space. Natural integral structure on H0 of Y omega 3 of Y. And furthermore, we had our class that we wanted to realize it in étale cohomology, but this is about integrality in coherent cohomology. So how to relate this integral structure with the integral structure of étale cohomology. Okay, so the answer, and it will be the point of this talk, is to, so in this part is to, the answer to one is what I call the Faulting's lattice. And the answer to point number two is exactly the integral p-adic Hodge theory. So whose purpose is precisely to relate the integral structure of coherent cohomology to the one in étale cohomology. Okay, so these are the main two difficulties, and which are exacerbated by the fact that when you have deep level at P, you don't have a natural integral model of your Shimura variety. So in this talk, I will tackle these issues. Okay, so first, let me try to motivate the answer to one. So for the Faulting's lattice, So again, so you might, the naive answer to one is to keep the same integral structure. So consider the lattice of sections of omegas in H0 of y, omega 3 of y, with p integral q expansion at the infinity cusp. But the problem is that there is no reason why this single cusp at infinity with totally multiplicative level structure on the Mumford object should be privileged with respect to other cusps. Okay, so you would like something more natural. So if here I have y with level at p, it maps to y naught. Y naught is the Siegel variety without level at p. So this is just the forgetful map. And now this has an integral model. Integral models I will denote by curly letters, y naught. And the point is that, so here I have my infinity cusp that determines the integral structure on on coherent cohomology for y naught. And here I have a bunch of cusps that map to the infinity cusps. C1, C2, and then here I have a privileged one, C0, which correspond to the totally multiplicative level structure. Okay, so this is what I mean by the infinity cusp for Y. So, and the answer, what Folting's tell us is that you should consider the Folting's lattice consists of all the omegas in H0 of Y, omega 3 of Y, that have P integral Q expansion at all the cusps Ci, so those above infinity, which corresponds to just different level structures at P on the Mumford on the Mumford object. Okay, so now let me state geometrically what this means. So again, take this point of view where you have y mapping f, I will denote the forgetful map to y naught, which maps to the integral model y naught, and this I will denote by pi. So since f is finite et al., you can identify the pullback of the differentials with the differential of y. And in particular, so this implies that when you push forward the differential of y to y naught, well, this is the same thing as the differential of y naught, but tensored with f star and then the constant sheaf over qp. And this one, you have a natural lattice inside, which is the differentials of the integral model tensored with the push forward of the constant sheaf from y. And so now when you take global sections, you see that H0 of y naught omega 1 y naught tensored with ZP with pi star ZP lies inside the H0 of 1. Sorry, so here maybe I put an I, it's for any I, and here maybe I take a 3. Yeah, so H0 of y omega y naught 3 lies inside this, and this is, with a little bit of geometry, this is the Faltings lattice. Okay, so so this is, in my opinion, the natural integral structure on coherent cohomology for y. Okay, for the Siegel variety with deep level at P. Okay, and so what is how do you check that something lies in this lattice? Well, you have the brute force approach, which is just to compute the Q expansion at different cusps. But there is also an observation that is due to faultings, is the fact that if omega lies in H0, y, omega 3, y in the naive lattice, is in the naive lattice, this means just that that the Q expansion at the cusp C0 is integral, and omega is UP ordinary for UP, the Siegel UP. So UP is gamma 1 and P to the R, and then 1, 1 PP, gamma 1 and P to the R. This is the Siegel UP operator. Then automatically, actually, the naive lattice and the Faltings lattice coincide in the sense that omega lies in the Faltings lattice. So it has integral Q expansion, P integral Q expansion at all the cusps above the infinity. Okay, and this is actually a rather simple consequence a simple concept of the geometric properties of UP, which is obtained by quotienting. So in the case of GL2, for example, and something very similar happens in SP4, you quotient by all the étale subgroup. And so you can proceed by induction in showing that omega lies in the Faltings lattice. Okay, so now we have identified what the natural integral structure on coherent cohomology is. And when we have something that is ordinary, we know automatically that it lies in this Faltings lattice. And E chi, actually, for the definition I gave you before, is UP ordinary when chi is ramified at P. Okay, so we are in precisely the condition where we know that our E chi lies in the Faltings lattice, and now we just want to build a map. A canonical map we will build, or functorial map in terms of X, so that it is Hecke equivariant from H0 of y naught, omega 3 of y naught. So this is just the Faltings lattice, ZP tensored OCP, to the H3 étale of y ZP3 OCP. Okay, so this I will call the Faltings map. So what the integral Faltings extension will do is almost, in a mathematical sense, almost produce this sort of map. Okay, so that maybe tensoring with OCP on both sides is a little bit too optimistic, but we will see what we can get, and that actually will be enough. Actually, since it's better to do geometry with proper things, we will build a map from X naught and here with log poles at the boundary to the same thing. So here X naught is Y naught Tor. So an integral model of a toroidal compactification of Y naught. We just want something that is non-singular. Just want something that is smooth proper over ZP. So smooth proper over ZP. Okay. And the log structure comes from the divisor of the boundary. All right. So now we are at the number 2, which is the integral Falting's extension. So again, this will be the key tool that produces this map. So here, this has not a lot to do with Shimura varieties. It's something that's completely general. So let me state it. So here I will take just X, smooth proper formal scheme over, say, CP. And so concretely, X is just the base change of X naught. And so, and now we're just going to build this sort of map from X. So with log structure, so maybe a log formal scheme. But so you have to add log everywhere, but there is obviously a story without log. So I may forget in the following to put log, but just think of everything that should be log. Okay. So now I release the key ingredients to build the Falting's extension, and this will be a rather modern approach. Okay, this will use pure sheaves from Schulze on rigid analytic varieties. Of Schulze, and then a little bit of sophisticated machinery, modern sophisticated machinery. But if you want a very down-to-earth approach, you can look at the 1987 paper from Faltings in the Mathanalan, where Faltings computes the Hodge structure of the cohomology of modular curves. And he has a version of these extensions which come from the universal elliptic curve above the modular curve. So in the case of Shimura variety, usually, at least in the PL case, you can formulate this extension in terms of the abelian scheme that is above. But we will take here a general approach because I think it is quite interesting that this exists in general. So now we'll list the key ingredients. So one key ingredient are cotangent complexes. So if AB are again log rings, there is an object which is called, so with a map B to A, there is an object L of A over B, which is an object in the derived category of A modules. I won't give the definition, but the key property is that this is very much related to one forms, the relative one forms, and if the key property is that if C goes to B goes to A, are maps then there is an exact triangle that is just L of the cotangent function of B over C tensored with A goes to the cotangent complex. So to A over C, which goes to the cotangent complex of A over B, and here plus 1. Okay, so this is called the transitivity triangle. And there is now a key object. This is the, so in what follows, I will denote by O is OCP, the ring of integers of CP, evaluation ring of OCP, and I will consider the Tate module of the relative differentials of O over ZP. This I will denote by O curly 1. This is known in the literature as a Breuil kiss and twist. It's a free O module of rank 1. Okay, and there is a map, the log from ZP1. So this is the tape module of mu p infinity, this p-divisible group, going to O curly 1, which sends ZP to the R, a compatible system of root of unity, to D of ZP to the R over ZP to the R. Okay, and the image, so the log is injective. And the image is rho times O1, Breuil twist 1, where rho is just a uniformizer of Z adjoint primitive roots of unity, is 1 minus zeta p. Usually people denote it by rho. Okay, so this this is the natural twist that appears in this integral p-adic Koch theory. It's not the Tate's twist, but it's the Breuil-Kissen twist, because the Tate module of the differentials of O over ZP is not really a Tate twist, but it's almost a Tate twist up to a multiplication by rho. Okay. So then another ingredient which is crucial in all of p-adic Koch theory is the ring A-inf. So O has a tilt, O flat, which is just the limit, the inverse limit with respect to x goes to x to the p of O mod p. And A-inf is the ring of vectors of the tilt. And there is a sort of a canonical element. So first you have epsilon, which belongs to O flat, which is just the inverse limit of ZP to the R, where ZP to the R are primitive P to the R roots of unity. And then I can take a Teichmüller lift, which lives in A-inf. And you can consider the element that's usually denoted by psi tilde, which is epsilon to the p minus 1 over epsilon minus 1. And you have a map, A infinity, theta tilde goes to O, which is reduction modulo psi tilde. So this is a surjection. Okay, so in the kernel, yeah, it's generated by this psi. There is a more canonical sort of definition of what this map theta tilde is, where you don't just say you don't just pick an element psi tilde and you just say that it's reduction modulo psi, but you prove that the kernel of this map is generated by this psi. But I will just take this very down to earth approach here. Okay, so now I have all the ingredients that are needed to define the Folting's extension. So to define this extension, we assume that x is the base change. So recall x was over OCP. So this was over OCP, is the base change over formal scheme over ZP, or really any finite extension of QP will do. But let me just assume ZP, since in the Siegel case that this is what happens. So straight letters indicate the generic fiber of the formal scheme. Okay, so X, so X is the generic fiber of the formal scheme X, and so now maybe I forgot to mention, but on X, on the pro-Kummer et al. Side of X, there is a period sheaf that is called, usually denoted by O hat X plus. This is called the completed integral structure sheaf. This was introduced by Schulze. But it appears in some version of course in Falting's work, and so the pro-Kummer et al. Side has a basis of affinoid perfectoid field. So if U goes to X is affinoid perfectoid. So take a presentation of U as say SPA of Ri plus, then OX hat plus of U is going to be the direct limit over Ri plus, and then you take p-adic completion. So this, okay, so if you want details about what these objects are, you can consult, the 2015 paper in Forum of Math Pi of Schulze, which presents this object in a beautiful way. But so I will sort of use this as a block box, at least in this talk. So now we can lift the key point is, since we have assumed that X was the base change of X0, we can lift X as a formal scheme over A-inf, just by taking X naught and then base changing it to A-inf. So this is sort of, the key tool needed to define the Falting's extension. And this lift, I will denote it by X tilde. Okay, this lives over A-inf. And now we have a map of rings. So OX tilde goes to OX. This is just reduction modulo Xi tilde goes to O hat X plus. So I have this map of O hat X. So I have this map of rings. So I have in the derived category of O X hat plus modules, I have the following exact triangle. So OX over OX tilde tensored. So I take also derived completions. So with OX hat plus goes to L hat of O hat X plus over OX tilde goes to L hat plus of O hat X plus over OX. Okay, so, and then here plus one. So I have this exact triangle, and now there are key computations which basically reformulate results of Fontaine, classical results. So key facts and the formal properties of the cotangent complexes is that you can compute the left-hand side. So you can compute this side, but also this side. And this side will be an extension of the left side and the right-hand side, and it will be Felting's extension. So now if I compute the right-hand side, I get OX hat plus over OX is canonically isomorphic to OX hat plus tensor omega 1x with log poles. Okay, so this over OX. And so this is first bullet point, and the second bullet point is this one. It's canonically isomorphic x tilde hat OX plus to, well, O hat X plus, but with the Breuil-Kiesel twist. So this just means that I tensored OX hat plus over O with the Tate module of the formal differentials with O of 1 in degree 1. Sorry. This is in degree -1. So they're both concentrated in degree -1. And so the consequence, if I denote by H, the cohomology in degree -1 of this cotangent complex, so I'll denote it by E plus, as in Felting's extension, I get an extension of O hat X plus twisted by 1, E plus, and then O hat X plus, tensor omega 1x log 0. Okay. All right, so this is the integral Felting's extension. The integral Felting's extension. Okay, and this extension allows you to build a map from the differentials of omega 1 to the Procummer et al. Cohomology of OX hat plus. So taking derived global sections, so taking R omega x and, sorry, maybe R gamma x Procummer et al. And cohomology, you get the following. You get the map from the H0 of x omega 1 x log to the Procummer et al. Cohomology of x with coefficients in OX hat plus twisted by 1. But this is the same thing as the Kummer et al. Cohomology of x with ZP1 coefficients. So this is Felting's almost primitive comparison theorem. So going from the et al. Cohomology of OX hat plus to et al. Cohomology is the key point. So it's tensored OCP, but this is an almost map. Okay, so it's only a map after you tensored the left-hand side with the maximal ideal. Okay, and the Kummer et al. Topology, the Kummer et al. Cohomology of x is just the one of the open ZP1 tensored OCP. Okay, so this we built a map from omega 1x to the et al. Cohomology as promised, but it's the omega 1 and not the higher omega I. So how do you build a map to higher omega i's? And the idea is just to take wedge power of the extension that you got before. For higher degrees, take wedge powers of the extension E plus. So as before, you will get a map from omega ix. Sorry, I forgot a key point. So this was a Breuil-Kiesel twist, and here I put the Tate twist. But this is incorrect. You cannot change from one to the other. You have to put a rho inverse here, OCP. Rho inverse OCP. Okay, so this is important. there is this row inverse. And so now you build again a map from H0 of x omega ix to Hi et al. Of y zpi, and then tensored with rho minus I, because here there will be an ith Breuer-Kissing twist, OCP. Okay. So this is not what I promised, because I assumed X was smooth proper, which is not the case for Shimura varieties with dip level at P. But so what is the trick? Again, the trick, as you would have guessed by now, it's due to faultings. And it is, so when you have this extension, uh, you have this faultings extension, you just tensor it with pi star ZP, which will be locally free. And then formally, you will get the promised map with the important difference that it's not an actual map, but it's an almost map, which becomes an actual map after you tensor with the maximal ideal of OCP. So summary, you get an actual map from, in the notation before that I gave before. So you get a map from y naught of omega 3 y naught log tensored with pi star ZP goes to, so this is tensored over ZP with the maximal ideal of CP to the H3 et al. Of Y ZP3, and then here you get rho minus 3 OCP. Okay. So it's not exactly what I promised, because what I said before is that here I had OCP and here there was no rho. Okay. But the key point, the key properties of this map is, first of all, it's very functorial. So after inverting P, it is Hecke equivariant. And retrieves the canonical Hochstate decomposition. Decomposition of, say, H3 et al., but any really in any degree. So the key is that after inverting P, it is Hecke equivariant and retrieves the canonical. And moreover, since you have, I use the log cotangent complexes, but you also have the non-log version, and you have a map from the non-log version to the log version. And so it is compatible. It is also compatible. Sorry. It is compatible with taking residues. And the residues on the right-hand side is just mapping to cohomology with support in the boundary. So it is compatible with taking residues. And so when we take, after inverting P, so the consequence of this is that after inverting P, the image of E chi, so seen as an element of the faultings lattice, belongs, so is the class omega chi et al. Here again, we're using the Manin-Drinfeld principle. Here we're saying compatible with residues, they both have the same constant terms at the cusps, and we saw that the map to the boundary, so the constant term map was injective, so they had to be the same. And so this means that the image of E chi tensor an element X in the maximal ideal actually belongs, since it was rational, since the class was rational, belongs to the H3 et al. Of Y, what was it? Yeah, ZP3 tensored with rho minus 3 OCP GQP. So if P is large enough, this will imply that E chi will belong to the H3. The image of E chi will lie in the H3 et al. Of ZP3. Okay. This is because you can descend the coefficients on the right-hand side, and here you can take X to be as small as possible. Okay. So the valuation of X as small as possible. All right. So then this implies, so the image of E chi, which was omega chi et al. All right. So this concludes the upgrade of omega chi et al. To an integral class. Okay. So the key was really to have this canonical integral map that's going from coherent cohomology to étale cohomology, and identifying this Fulting's lattice, which does not care whether you have good reduction or not, as long as you have a finite étale map to a variety that does. And this for Shimura variety is always the case. All right. So now let me go into the applications. But first, are there any questions about what I did?
No, it seems no question.
Okay, very good. So I'll proceed with the applications. So first, the application number 1 is Oda's theorem for more general Shimura varieties. So one of the key tools in explicit reciprocity laws, at least in Hida's family, in Hida families, and this this was the hidden subject of a question by Eric Urban in my first lecture, is this Oda's theorem, which says that when you take inverse limit of the étale cohomology of the étale cohomology of modular curves, this is geometric étale cohomologies, and then you take ordinary projector, or rather its dual, E-ord, and then you take inertia invariance. This is isomorphic to a module, the module of lambda-adic Hida families. Okay, this is M-ord. So Hida family. So, and here I forgot to take ZP breve. So this is the period ring. So this representation, when I take inertia covariance, becomes unramified. I tensor it with ZP breve, which is the valuation ring of the completion of the maximal unramified extension of QP. And if I take GQP invariance, then this becomes the same thing as ordinary modular forms with coefficients in ZP. Okay, so this is Oda. So these are really something defined on the Q expansion level, as you know, you're interpolating the Q expansion of modular forms, and this is really classes in étale cohomology. And so this is precisely the point of integral periodic Hodge theory, is to relate the two integral structure. So it's no surprise that we get under this general framework that we get a very similar statement. So I'm going to state the theorem in the case of Hilbert modular varieties. So now I have y1 of n frac and then p to the r. So this is the Hilbert modular variety, but with level at p, that is the one that's relevant for the ordinary level structure. So this is chi1 and p to the r. Okay, so as was stressed by Thiluin in his first talk, so if you put a 1 here, you would consider nearly ordinary families. But I really want ordinary families because I want to take inertia coinvariance. Okay, so then the interesting cohomological degree is, let's say, so this is over a totally real field f over q totally real. So, and let me say that the degree is, say, d. Then you can consider the module h infinity of minus minus, which I call h infinity of minus minus, because here now you have to worry about torsion, unfortunately. But, so how is it defined? Again, as before, you have a version of the ordinary projector. Then you take the inverse limit over r of hr et al. Of y1 and p to the r, zp to the d, inertia coinvariance, but this is the torsion-free quotient of the inertia coinvariance, okay? Then, okay, so this is h infinity minus minus, and then you have h infinity minus
The
minus.
homology degree is R, not it's
Oops,
D.
oops. D. Thank you so much. Yeah, D, not this R. I'm not changing the degrees. Yeah, so otherwise it would be 0 very quickly. Okay, so the degree is D, as I said. And so I have this module, which is the complete analog of this module here. It's just that I'm taking inertia coinvariance a little bit before. Then I tensor with ZP breve and take GQP invariance. And this is the module of ordinary Hida families. Okay. So this is joint. So this is theorem. This is joint with Chris Skinner. Okay. So again, the key tool is the Faulting's extension and also a map that goes in the other direction, which was constructed by Zavialov, sort of by inverting the Faulting's extension map. Okay, so this is one of the application. We have a similar statement in the Ziegel case, but in the literature, except in the case of SP4, where it was proven by Urban, we couldn't find in the literature the fact that the spin representation, say on GSP2G of a Ziegel modular form has inertia coinvariance. So this is sort of the obstacle to getting a statement that's exactly like this in the Ziegel case, but you have the two maps and still you get something out of it. And lastly, let me mention the application of the Euler system built. So this is the Euler system built out of the classes omega chi et al. With the method that Chris outlined in the GL2 case. Once you have constructed these integral classes, you can build this Euler system using this relative cohomology exact sequence. And So one that I particularly like is that you can prove with R ORD with the surjection of R ORD to T ORD. So the surjection R ORD, this is the big ordinary deformation ring of some modular rho bar, and this is T ORD is the Hida's ordinary GL2 Hecke algebra, localized at the maximal ideal GL2 Hecke algebra. Localized at M corresponding to rho bar. So this is a general surjection. If rho bar has big image, so this means that rho bar is non-dihedral. So this means that the ad naught is the ad naught of rho bar is residually irreducible. Is irreducible. Sorry, it's already reducible. You can upgrade it to an equality. You can reprove that R ORD is equal to T ORD. Okay. So this was actually Weil's initial strategy to prove his R equals T theorem, because he wanted the surjection. So he wanted to build an order system out of Benenson Flach, or rather Flach classes for the symmetric square of the Tate model of an elliptic curve. But there was a gap in his construction, and then he invented another great piece of mathematics that was his patching method with Taylor to prove this R equals T theorem. But so this gives an independent proof that doesn't rely on patching using the order system bound. And so the sort of the unfortunate thing is that we really have to assume the ordinary condition here, which is not enough for Fermat, for example. Not enough for Fermat. Because if the Frey curve, which doesn't exist, but has good reduction at 3, then it's super singular at 3. So the method of this Euler system, which is really in the ordinary case, do not apply. And so also combining our Euler system divisibility divisibility with Urban's divisibility using Eisenstein congruences. But funny enough, it's sort of a dual approach where he considers a Klingen-Eisenstein series on SP4. Using Eisenstein congruences, we get the two variable Iwasawa main conjecture. So I'm sorry I didn't have time to state the results more precisely, but hopefully this will give you a taste of what you can prove using these methods. And I'll refer you to the preprints on my website if you want to look at the details. So I think I'll stop here. Thank you.
Thank you, Marco. Yeah, are there questions, comments?
In your application to R equals T,
Yes.
do you have the same hypothesis as Y, or do you have weaker hypothesis?
So about the row bar restricted to Q P adjoint zeta P, that sort of hypothesis?
No, I mean, there was this approach of minimality, for instance.
No, yeah, no, it's really the only thing we need is the big image to apply the divisibility, and then we use the surjection R to T as a sort of as an analytic class number formula, which gives you the numerical coincidence.
Okay, so if there is some bad primes in the levels.
It doesn't matter at all. Yeah, the tame level doesn't matter at all. Yeah.
Marco, I have a very naive question that the author's theorem gives you the proof of some USM main conjectures. So in Hilbert modular form, in Hilbert modular case, have you thought about that? Is it going to give you the USM main conjecture proof?
That's a very good question, and the issue is that in the Hilbert variety, so it's defined over Q, and the costs are defined over Q. So 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 you don't see the characters over F. So it's not. So I have no unless you have some way of taking into account. The sort of plectic structures in the conjecture of Scholl and Nekovar, I really don't see how you would imitate the Oda's proof for GL1 because of this fact that the costs of Hilbert modular varieties are defined over Q.
Yeah, thanks.
More questions?
Hi, I wanted to ask, you're now constructing these classes with constant sheaf, and like the King's Loeffler-Zerbes or Ley-Loeffler-Zerbes, they have this moment map where they build the Bellinson flag for like T-sim type of sheaves. Do you also have this notion of moment maps, or do you require?
So yeah, so that's an excellent question. So it's so they have this whole theory of moment map because in their explicit reciprocity law, they do the computation at crystalline points. So they need to go to higher weight. But so in the explicit reciprocity law that we prove, we really work for trivial coefficient systems using results of Kolmez and Nizio. But so it's a different approach. So we are basically able to deal with the bad reduction or lack of integral model to compute the explicit reciprocity law. So we can do the explicit reciprocity law just from the point of view of weight 2. So we do not need the moment map to go to higher weights. So it's really, yeah. But you can go to higher weights by p-adic deformation.
Thank you.
More questions, comments? Okay, it seems not. Let's thank the speaker again.